All right, looks like we got most people back, so hope you had a good lunch. Hope it was delightful weather out there, so hope you got a little bit of fresh air since we're going to be in here for the rest of the day. Last year, I got kind of nominated and put into the position of discussing more on the disaggregation or hyperaggregation. And so what we've done is I'm both a track organizer and the first speaker of said track, so that way I get to wear two hats. First is going to be Yttibrium, myself. After that, we'll have Newtonics come up and talking about the hyper-converged systems. Then we'll be bringing up Intel and talking about what are the new compostable architectures and how does that affect us. And at the end, Snowflake will come up and discuss what disaggregation. We'll do the same format as we did in the first section under Stephen, where we'll hold all the questions until such time as we all come up as a panel at the end. So my name is Per Brashers. I started a small consulting company focused on the hyperscale use cases and needs. And so I spend almost all my time dealing with either providers or consumers of hyperscale solutions. And so what I'm going to be talking to you about today is why do I have a downward sliding swimming fish here, right? I've obviously got one curve, which is what our bank accounts should do, and another curve, which is what our bank accounts actually do, right? But what I'm going to really talk about is there's an inflection point right there that says there's a flip. And what happens is, am I actually saying this is business growth and IT budget? Well, that really depends. Different business organizations will have a different reason to flip. So in that sense, this is completely bull because what these two drivers are could easily be this. But if you have a business unit like inside of Goldman Sachs, you're obviously a very traditional business, but they have a hyperscale unit, and they're on the other side of this flip. Now, when I was back at Facebook, we would call this the difference between working in Newtonian physics and working in Einsteinian physics, right? In this world, I could cope with looking at numbers of machines. I could actually count and do something. When I got over to there, when I walk into the office in the morning, I was looking at heat maps of thousands of machines and deciding on the yellowness or redness of the world. Do I get a cup of coffee or am I sitting down to start figuring out what's going on? So there's a very big difference in the implications when you cross that flip. So I basically say somewhere in this right-hand side, or left-hand side to those of you who are looking at it, is the traditional enterprise and some of the Web 2.0 guys. These are not yet hyperscale, but there's a lot of them who are pushing up against that flip, and they're running their business very much as the traditional style. And then you've got the other side. You know, the example I gave you is Goldman Sachs has a business unit which is specifically on the other side of the flip. And then you've got the Googles, Facebooks, Amazons who are definitely on the other side of the flip. So what does that really bring to us? It brings us two entirely different market segments. And that kind of talks about these guys, they're very process-oriented. They want to know if I build a car today, I can build that same car tomorrow. And they get really very, very process-oriented. And this will affect even their IT infrastructure. And over here, they're all product-oriented. I don't care how you get that product out, ship it, right? We'll fix it later. Quality doesn't matter, quantity matters, right? And so there's a big difference in that. These guys talk about Capex. They are really, really concerned about how much does it cost for me to get the equipment necessary to service this work. And over here, you almost never hear them talk about Capex. They look at it and go, 500,000 servers running 4 watts more than those 500,000 servers. I'll take those. Because of 4 watts at that kind of account means a lot of money on a recurring basis, i.e. your electric bill. These guys do some ROI, right? If I buy this, is it going to make my business better? Is it going to help me sell something? Am I getting a better widget? And these guys go and do strong TCOs, right? Including power budgets, including decommissioning costs, including burn-in time. All kinds of details go into these TCO models. And they're different for each of them, right? So you talk about the 8 hyperscalers. They all look at TCO differently, and they all get their own reasoning. And that's because they make money differently, right? In the case of Facebook, you make all your money, or Google for that matter, you make most of your money off of advertisements. If you talk about Amazon, you make your money off of sales and doing delivery and having drones landing packages and things. These guys treat their IT infrastructure like pets. They love them, they give them names, they do all these wonderful things, and these machines are precious. Over here, my barcode is the only thing I know about it, and they're treated like, if it fails, you throw it over your shoulder and you stuff another one in and go, right? They don't give them any kind of value aside from it services my need. We do tailored servers over here. You go and say, I want specific CPU with this exact memory configuration and this much SSD, and this is how my application, and we go through, you know, the old IBM Red books, and we step through the process. And over here we say, you know what? If I have to have multiple SKUs in my back room, somebody's going to go and pull the wrong SKU and stick it in the slot, and that's going to affect my business more than if I have 1 to 5 SKUs total, and I merely simply stuff them in there, and they don't run at 100%. They run at 90, 85%, right? That's a value to the lack of the SKU. That's why they deal with low SKU count. Nameplates and bezels, you know, you see logos here. You see people actually understand where they bought it from, and over there, it's vanity free. You see, I took a motherboard and I mounted it on top of another motherboard, and I put it on a pizza box and I stuffed it in, right? So there's a very big difference in who they buy from and what they're buying. So there's another big change when you step across this flip, and that is you design things on the enterprise in a meantime between failure method, right? Things are built to be really strong, really capable, as opposed to the mean time to repair. I want everything disaggregated. I want all the pieces individual. Don't put smarts down on a disk drive. Make everything unique and dumb as possible so that I can disassemble it and go, that's the problem, and fix it in near real time, to borrow from Stephen, right? So that means these guys buy the Rolls Royces, and those guys buy the old Willis Jeeps and say, I can fix a carburetor with a bobby pin on the road. That effectively means there's a split in the market between who does converged infrastructure, who does their scale up and who does disaggregated or scale out. Now, obviously, there's some lies to this because there may be scale-out infrastructure within a traditional scale-up enterprise, et cetera. But from a general point of view, that's kind of a split in between the pieces of that market. So everybody loves the being able to plot something out because you can actually tell where things are. So I go here with the definitions of converged means I have some level of node customization. This node does this job differently than another node. And so this node has special CPU, it has special DRAM, it has NVDIMMs in it, whatever that may be. And then disaggregated, that node effectively can serve any purpose. So if you go into Amazon and you see that you've got your AWS instance and you actually read your end user license agreement, you would realize that if their web store started taking a hit, they have the right to kick you off and start moving your load to some other place and using that compute for themselves. So that kind of elasticity is what you get from being able to do a disaggregated or nodes serve a generic function. That also drives that I want one SKU in the world, right, and one for everything. Scale up where a node performs the job as an entirety, right? It is start to finish on a node. And that you see a lot. And so in this case, you could argue whether a node was a rack. You can argue if a node is actually like Cray, like where it's a row. But, you know, node said in heavy quotes on here. And then scale out, of course, node is just I perform a piece of the job, i.e. Hadoop. So basically, I laid out some things on here and said, you know, where are some of these guys, right? So Hadoop is basically the ultimate of scale out with disaggregated. You can disassemble the hard drives and get them away from there. You can take the CPU complex and memory and separate it from the NIC. You can go completely disaggregated. Whereas you go up and talk about MySQL, well, you kind of need to have a little bit of design in the node. You've kind of got to know if you're going to handle 1 million IOPS off this thing. You pretty much are going to have to run on some NVMe device. If you want to try and do 400,000 ops, so you got to be kind of careful about how you design that. And so that's kind of where I sort of laid out different pieces to say where do the different bits of the market land. Looking at more of this, I realized I should have added a network piece, right? Because we talk about network here, and you talk about there's a Cisco and so on versus I'm doing ONI and I'm doing private no label switches and software-defined networking, et cetera. But really, I mean, we've talked about who they are, but the MTBF versus MTTR is really very interesting because of the implications to software, in the sense that in the guys in the traditional enterprise expect that their data durability is down at the device level, i.e. I have a RAID device, I have a storage array. I don't know anything about data durability, I just know about SQL queries or whatever I'm doing. And the storage has to take care of that. It's exactly opposite of the scale-out guys. They go, I'm going to erasure code this across 14 racks, and then I'm going to erasure code it down the rack so I can lose any node at any given time and not take a network rebuild, right? So localized erasure codes, or what we're now starting to be called 3D erasure codes. And same within the server platform. It's quite difficult to find in the hyperscalers any logo of a Dell, Oracle, et cetera, with the exception of things like their billing system or the old school reporting system that goes out to advertisers saying, here's how much advertising you actually run. So there's always pockets of traditional IT for those use cases that actually require them. So we've come to the end of Moore's Law. That's something that has been debated, and there's lots of variance between, oh, no, we're going to go again, we're going to have 3 more ticks, et cetera. But the reality of it is, Intel has already fallen off the tick-tock cycle once. Sorry, Mohan. The next place we can go, we're getting one more size cycle. And the next place we have to go is to 3D transistors. 3D transistors is going to be a huge expense, and now we're talking about Intel makes all of its money by time to volume, right? So time to volume has been the way that it has grown for dozens and dozens of years, and now we're talking about volumes aren't there. We're building special processors for some of the hyperscalers. We're seeing tailoring of the processors. We're seeing losing space on the processor, so we're trying to kick SATA off so that we can actually get more physical space. So we're not going to see another round, maybe 2 rounds more, but NAND, the power and heat dissipation that you're going to see off of the CPU or off of NAND isn't going to come down by an order of magnitude. It may come down by like a factor of 4. That's pretty much it. And then megahertz is not going to go anywhere. We've been stalled on megahertz, so we're talking about the only way we're going to get more throughput is to go to more cores. So if you think it's crazy to try and write threading software today with dealing with 30 or 40 cores on a machine plus hyperthreading, so you have 80 virtuals, start thinking that those numbers will double or triple, et cetera, as we end up not being able to take it out of the physics anymore. And then size is always an issue, right? Because if we're getting into building SoCs that are the full size of a wafer, your volumes start to drop because you have any kind of issue. You don't cut the wafer and you use the whole thing. Any issue at all, you lose the whole thing, as opposed to today, you cut it and you'll lose the piece that was damaged, but the others still make it through the assembly line and on out. So that gets a very interesting cost analysis of trying to produce the next round of chips, et cetera. Areal density, right? A while ago, the hard drive manufacturers tried to do this concept where they would put some NAND on the drive and then say, okay, I can maintain my IOPS per terabyte and it's going to be great. And the truth of the matter is, you're never going to be able to guess the correct ratio. If you did guess the correct ratio today, guess what? We're going to write a couple of more lines of code, we're going to push again, and guess what? Now we're on the wrong ratio. So having it down at the device level doesn't work. Putting it up in the machine level and making a system out of it where I can do my work between a fast and a slow device, that makes much more sense. So SMR, we saw SMR get released into the market almost full 2 years ago. About a year ago, we saw all the hyperscalers say, okay, fine, I know that I need to do this. I know that this is important, so I will go ahead and write an SMR driver. Well, they all failed. And they came back to the hard drive manufacturers and said, why are there so many corner cases? Why is this so complex? And basically it comes down to, it's an electrical mechanical device against a bunch of 22-year-olds who know how to write Java. So who do you think is going to win that game, right? So SMR could be fixed. We need a driver for Linux. We need some work done to it. But frankly, it sits in T10, T13, and is going to be another 2 years before we actually get any progress out there. Heat-assisted magnetic recording, it's not going to work. Even if the vendors claim that they've got something they're going to ship, and they say that we have actually got a drive, the issue is it's going to be such low volumes that they're never going to recoup their losses for having designed all this stuff, and they're going to basically go out of business. So that means that Samsung is ostensibly correct, that we should be, say, investing in Samsung because Samsung is going to kill the hard drive industry. And if you want to talk about insanity, bit pattern media, where I take the platters and I actually etch them just like I would a chip, and then I try to lay out little islands to go do my writing on, I just made the cost go from I flow across my media with a flow mechanism versus now I'm etching media, so why don't I go ahead and buy NAND? It's going to be the same cost as NAND, if not more. So there are some old players who have stayed the test of time and are still going to be alive and going to be interesting. Tape managed to break away and has bifurcated the industry. If you look at LTO, you're looking at a dead piece of industry. If you look instead at the newer stuff where they managed to get rare earth to stick to flexible media, that means that they got rid of the layer of clay in between the ferrite oxide and the head, so now the heads actually can contact the media. They then went to the VCR guys and said, hey man, can I buy that head off of you? And so instead of just being 4 heads sitting running like your 8-track tape used to, they now have fly heads running, so you've got your data striped this way. And so it's easy to see the roadmap for tape is roughly a 3 to 4x more dense than they are today, which means roughly 3 to 4x faster throughput, and already at a few hundred megabytes a second, a tape already outruns a disk by a long shot. And so the only reason that tape isn't dead is because we still need to keep the bytes. And at the end of the day, the problem with tape is I have a namespace over here. I may go from my Spark instance to a HBase instance down to a Hadoop, and I want to keep this data, right? This data has value, otherwise I would have thrown it away in the first place. I might not know what that value is, but I think it has value, and so if I keep enough of it, it will of course grow and have value, so I'm going to keep it all, right? That's how it works, right? But if you then say, I need to eject this stuff and stick it on tape, you lost it from the namespace. You no longer know you have it. It loses its value. And so tape has always been an evil player where I want to try and derive value out of data. Optical is very interesting because it turns out that optical was limited by two main factors. One was, as soon as we got to 4K video, we weren't going to see anything more. That was the outlook for the whole market. No, nothing would ever have to go faster. So at the point where the engineers had figured out how to make optical go as fast as 4K needed, they were out of jobs. They were on the streets with signs saying, I developed optical, help me, right? Along come the hyperscalers who say, yeah, well, I can't really eject this stuff out onto tape because I lost it from my namespace, but I really actually need something that's, like 2 cents a terabyte, please. And yeah, it can be slow. I can have time to first byte in minutes. I can even have streaming rates, at sub-gigabyte a second. But I need to have a library of this stuff. I need an acre of it because, well, the platters are only 300 gigs apiece. So along comes OAI and goes, well, I can fix that, and I can fix that speed too. We're running about 1/10 of the speed that we would, and by the way, these guys in the physics lab had figured out how to shoot 2 lasers at each other, and there's a reflected laser that comes out of the end of that, and so I don't actually need a head anymore. I can actually do laser shooting on the outside of the media and be able to get a much smaller laser, if you can believe it, so I can get you faster, better density, and I can get you a roadmap that says 500 gigs in 2016, 750 in 2018, and a terabyte in 2019. Okay, optical has some kind of interesting runway. Provisioning and management tools. How many of you have met 5, 6, 8, 10 tools in your lives and realized every tool is unique? If I buy a Symmetrics, I get a Symmetrics manager. If I buy a NetApp, I get a NetApp manager. If I buy a white box, I go, I'm going to use Chef and Puppet, right? And then I get a team that fills this entire stage of people who start learning Chef and Puppet. So there's teams out there who are starting to realize we need a uniform management. We need to be able to deal with our equipment and our data centers as what they should be. And then we've heard of 5D storage, the holographic storage. We can shrink everything down to a sugar cube. Cold fusion is back, guys. And I just got another article about, oh yeah, come and work with this startup that's going to be able to put 300 terabytes on a 2.5 millimeter disk. Right. So the trends are basically JBOD's cool, right? JBOD was cool when we had application level data durability. Well, we have application level data durability. If I don't have JBOD, I actually affect my CPU complex while I'm doing a servicing event for something like storage. I need to throw my PCIe card off. Guess what? I have to yank that server out. I have to do something to it. So JBOD's awesome, right? NAND is actually not only getting cheaper, but it's starting to learn that it needs to be faster. And I don't mean faster like give me an NVMe device with 1 million IOPS, but I mean instead of giving me a device that has 4 I/O lanes and 2 read channels, they're starting to realize we actually need to be network balanced before we can get anywhere. So the newer generations, you're starting to see much more leveling, much more balancing, and you're starting to see things like ARM processors down near the NAND to try and do repairs, housekeeping, etc., without having to affect the host I/O. And then 3D erasure codes, you know, what's our next thing? What happens after localized erasure codes? Microservers aren't that micro anymore. The power envelope for the Xeon D beats the power envelope for ARM, and yet I still get all the neat libraries, all the things that I need, and I get binary compatibility. So I don't have to have 2 management systems. I don't have to have 2 binary pools. I don't have to have 2 sets of staff, right? So, and then the motherboard virtualization, which Mohan will ostensibly be talking about, it's becoming to the point where you can actually do a software-defined motherboard. Blast zone, however, becomes a question. So you don't really want to have a 10 petabyte, 4,000 server single blast zone, right? If you do that, you would do it like Oak Ridge National Lab did, where when the Cray shut down, the back EMF onto the power grid burned out half the city, right? So that's not good juju, right? You want to have some kind of smaller containment. When IETF said, no, we're not going to do 25 gig, that was the biggest mistake in the universe, because 25 gig is wonderfully balanced for device-level virtualization inside of a virtual rack and gives me this wonderful, wonderful cost, because I can take a single PHY off of my 100 and run it out to each of the devices, and I get my 25s, quote-unquote, free. So they just literally missed it on that one. Transport versus protocol, we're starting to see what happened to the car industry when Teslas and Fords and so on showed up and said, oh, my car is actually an Ethernet. It's raw Ethernet, so all my devices speak raw Ethernet, and then you, of course, get hackers come in and go, you don't have any verification. I can pretend to be the oxygen sensor. So this is definitely a very interesting space, because people are starting to do ATA over Ethernet projects again, and that's meaning that you need to become aware of a network separate from the transport. Is NVMe always required to be on PCIe? No. There's difference between the protocol and the network. And then decreased latency, basically this software-defined networking. Boy, I should have had some water. Applications, data integrity is moving further away from the data, and that's a good thing. That means that we can talk about compostable architectures, which are very, very easy to debug, and that means that a lot of value add goes home. And then not every workload is embarrassingly parallel, so AMD will always have a fit. I have a CFD workload, uniquely single-threaded. AMD will win that business every single time in a bake-off, because they chose to go thread optimization where Intel chose to go core optimization. So there's a big difference in those two. And then data flows, right? Processing, and we talked a little about recycle, but I don't think we do enough to do downsampling, right? We really need to work as an industry to talk about how can we downsample and still actually have usable, viable data. And then data governance, right? Many of these countries have rules that say you can't leave my country with this data, and it's becoming a much, much bigger issue. The African Coalition of African Nations is voting this month or next to basically say they're going to adopt the German standard, which says nothing about anything that belongs to my citizens is allowed into any other country. Oh, very interesting. So that brings me to the end, and I thank you. Again, we're going to go ahead with a method where we will throw in all 4 presenters and then have a panel at the end. So with that, it is Binny.